Swayam Prabha. Digital India. Educated India.
Namaskar. So, in last class we were discussing about the state variable, and we also saw that if you have n order differential equation, so you can convert that nth order differential equation into n first order equations, and then we also discussed that these differential equations which are first order in nature can be considered as a state equation, and we can define the various state variables, and accordingly we can sum up the state variable into a equation called state equation. And we also stabilize that the equation you can write in the matrix form as x dot is equal to Ax plus Bu. We also discussed that the output equation we can write in the similar fashion, and we can write y is equal to Cx plus du. So, this is what we discussed in the last session. Today we will discuss about the state diagram, and before going to the state diagram, let us first understand the transfer function in case of multivariable system. That means, if you have multiple variable in the system, how you will find out the transfer function. Now, the definition of transfer function is easily extended to a linear system with multiple input and outputs, and this type of system where you have multiple inputs and outputs, we call them as multivariable systems. Now, if a linear system has p inputs and q outputs, the transfer function between jth input and the ith output can be defined as g I j in S domain equal to y I s divided by r j s. Now, this is applicable when the other input variables are 0, that means r k s equal to 0 for any value of k not equal to j. So, we are considering one input at a time. Now, this is only for considering the jth input in finding out the transfer function. If you consider all the inputs, say there are p inputs, if you consider all the inputs, you can write the output, transformed output in S domain as g I 1 s r 1 s plus g I 2 s r 2 s and so on up to g 1 p s r p s. Now, similarly for various outputs, that is I ranging from 1 to q, you can write these equations, and when you compile, you can write in matrix form as y s is equal to g s r s. What is y s? Y s is the number of outputs. So, it will range from 1 to q. So, that is why the y s will be q to 1 output vector. Similarly, r s is the p to 1 input vector. Then what will be the value of g? G will be q into p matrix having the individual transfer function corresponding to relating the input and output of the number of components we have in the inputs and outputs vector. So, this is how you define the matrix which contains the multiple output and multiple input. Now, let us see when you have the multiple input output, that means we have a multivariable system, how we will find out the transfer function. So, if you see this block diagram, here you have one multivariable system where are multiple inputs starting from r 1 to r p, and outputs are from 1 to q. So, in short you can say that it has a vector r as an input and vector y as an output. So, now if you are asked to find out the transfer function which is having a feedback loop, how we will define in case of multivariable input. So, this r s is multivariable input. So, you will have r as a vector as an input and y as an output containing the vector of q terms. Now, GS is the transfer function. So, you can see that this can be considered as a transfer function matrix, which we just saw in this case. So, what we can write? So, in this case, this is your the forward path gain matrix, this is your feedback path gain matrix. Now, if you find out the value of y s, you can simply write that is G s into U s. U s you can write as R s minus B s, and B s you can write as H s y s. So, as we discussed, y s is q is to 1 output vector, and U s, R s and B s are p is to 1 vector. Then G s and H s are q into p or and p into q transfer function matrices. So, dimension is given in case of G s and H s. So, for G s it is q into p and H s is p into q. Now, the objective is that we need to eliminate the intermediate variables, that is u and b. So, when we eliminate u and b from these three set of equations, we can write y s is equal to G s R s minus G s H s y s. Now, when you recompile, y s you can write as I plus G s H s. I is nothing but identity matrix. So, this will become I plus G s H s whole inverse into G s R s. Now, the transfer function is nothing but y s upon R s. So, if you say y s upon R s is nothing but m s. So, you will get the closed loop transfer function matrix as 1 plus G s H s whole inverse into G s. So, this is how you will get the transfer function matrix in case of multivariable system. Now, let us take one example. Suppose forward path transfer function matrix is G s given, and the feedback path transfer function matrix is H s, it is given. Now, we need to find the closed loop transfer function matrix. So, first we will try to find out the value of I plus G s H s. So, if we put the value of I is nothing but it is identity matrix. So, you have this information in your hand. G s H s is given. So, when you put the values and simplify, you will get I plus G s H s as s plus 2 upon s plus 1, then minus 1 by s 2 and s plus 3 upon s plus 2. Now, next is we need to find out the transfer function matrix. So, in that case, when we are finding the closed loop transfer function matrix, first we have to take inverse. So, when we take inverse of the I plus G s H s, we can simply write 1 upon delta into s plus 3 upon s plus 2, 1 by s minus 2, s plus 2 upon s plus 1, and then we put the value of G s. Now, the value of delta we can get from the matrix, and when we simplify, we get the transfer function matrix as s into s plus 1 divided by s square plus 5 s plus 2, and in bracket we will have one term as 3 s square plus 9 s plus 4 divided by s into s plus 1 into s plus 2 minus 1 by s, then 2 and 3 s plus 2 by s into s plus 1. So, this is how you will get the transfer function matrix in case of multivariable system. Now, let us talk about the state diagram. So, what is a state diagram? A state diagram is nothing but the extension of the signal flow graph, which we discussed in previous lectures, and this shows the state equations, so which we discussed, and the differential equation, because when you talk about the first order differential equation, that is nothing but the state equation we are talking about. So, state equation and differential equation can be shown in the extension of signal flow graph, that is nothing but the state diagram. Now, the significance of the state diagram is that it forms a close relationship among the state equations, the computer simulation and the transfer function. How? We will see when we discuss the state diagram in detail in this session. Basically, the state diagram is constructed following all rules of signal flow graph, which we have seen till now using Laplace transformed state equation. Now, the difference between signal flow graph and state diagram is the integration operation, which we have little bit difference as compared to signal flow graph and the state diagram. So, in this case, when we talk about the state diagram, let us first see how the integration operation you will define in the state diagram. Let us see, there are two variables x1 and x2, and these are related with each other as dx1 by dt is equal to x2. So, if you represent them in the state diagram, you will say that this is basically x2, this is x1. So, you can write dx1 by dt is nothing but s into x1. So, s into x1 will be giving you the value of x2. Now, this is for this. When you are talking about the integration, what we have to do? We have to first take the integration on both sides. We can write x1 t is nothing but equal to, the integration will range between t naught to t and x2 tau d tau plus x1 t naught. So, this is basically the initial condition which we have taken at time t is equal to 0, time t is equal to t naught. Now, if you take the Laplace transform, so as we know that signal flow graph algebra does not handle integration in time domain. So, what we have to do? We have to take the Laplace transform on both sides. So, we can write x1 s is nothing but Laplace of the integration from t naught to t x2 d tau and plus x1 t naught by s. Now, if you are doing the integration of this, you can separate this into two parts. So, you can simply write one integration will range between 0 to t x2 d tau and another is from 0 to t naught, that is minus, and integration between 0 to t naught x2 d tau. So, this can be equivalently represented with the help of the integration which we have broken into two parts, and then x1 t naught by s, which is the initial condition. Now, if you see the Laplace transform of this, you can simply write it as x2 by s by the definition of Laplace transform which we discussed previously. Now, next item which is left is Laplace of 0 to t naught x2 tau d tau plus x1 t naught by s. Now, since the past history of the integrator is represented by x1 t naught and the state transition is assumed to start at tau is equal to t naught, means we are transiting at tau is equal to t naught, that means x2 tau will be 0 before t naught. So, what we can write? x2 tau is 0 for the period between 0 to t naught. It means that this particular section you can replace by 0. So, finally, what you get? x1 s is equal to x2 s by s plus x1 t naught by s, which is valid for time t greater than t naught, because the period between 0 to t naught, the value of the initial condition for variable x2 is 0. Now, the equation that is we have just found, that is x1 s is equal to x2 s by s plus x1 t naught by s, is now algebraic and can be represented by the signal flow graph. How will represent? If you see this figure, you have two variables, one is x2 s, another is x1 s, and we are summing up here, that is summing block. So, at this point this will be x2 s plus x1 t naught and then it is multiplied by 1 by s. So, finally, you get x1 s as x2 s plus x1 t naught divided by s, which is nothing but the equation which we just derived in case of the integration which we just performed. Alternatively, you can also represent it in a less number of connections. So, say if this block is representing x1s, so 1 by s you can put in both of the cases. So, here when you sum up, you will get x2s by s plus t1 plus x1 t naught by s. So, both figures are representing the same equation. So, the advantage of this particular figure is that you need fewer element to show the equation which we just derived. Now, let us see how you will convert the differential equations into state diagrams. So, when the linear system is described by higher order differential equations, state diagram can be constructed from these equations. How we will construct? Let us consider one differential equation which is of nth order differential equation. So, that is dny by dt n plus a n d n minus 1 by dt n minus 1 plus and so on up to a 1 y equal to r. So, this is suppose you have got this differential equation and you have to convert this differential equation into state diagram. So, first what we have to do, we have to construct the we have to rearrange this equation as shown in this equation, that is we will write dny by dtn equal to minus of a n dn minus 1 y by dtn minus 1 and so on minus a 1 y t plus r t. So, what we have done, we have kept this as the left component and rest we have shifted to right side. So, we got this equation from the previous equation. Now, what we can see that the if you take the individual Laplace transform, you can write this as y s, this particular component you can write as s y s, and this you can write as s to the power n minus 1 y s and so on. So, you know that individual components you can represent as their Laplace transform. So, what we will do, we will this particular component you can replace with the Laplace transform of r t. So, we have now around total n element for one as the as the forcing function on the right side. So, these are generally considered as a node. So, when you represent them as node, how you will show them in the figure? So, we will see y. So, we have put one node as y, then next is s into y s. So, we have put s y and so on. So, we have got up to s n minus 1 y and then s n y for the last component, and then we add r. So, we have put all the elements which we have seen in the equation as nodes. So, what is s I y s? So, the ith order of the differential component, that is d I y by d t I, is nothing but s I y. So, for nth order component we have written s n y. Now, we have defined the nodes. Next, we use this equation to define the links. So, if you see the equation which we have just rearranged. So, what we can now see? We can see the connections. So, if you see this particular node, that is s to the power n y, which is nothing but representing this particular component, that is d n y by d t n. So, that means this will be the summation of all other components. So, r t does not have any component coefficient there. So, you will connect r with s to the power n y with only unit gain. Now, let us see this particular component. So, in S domain you can write as minus a1 y s. So, what will happen? You coefficient for this particular component is minus a1. So, what you will do? You will connect the y with s to the power n y with minus a1. Similarly, for this you can write minus a2 into s y s. So, s y s you see here, and this is connected with s to the power n y as with the coefficient minus a2. So, you got minus a2 as the connection, and similarly you connect all of them. So, what you get finally, that is s to the power n y is nothing but r minus a n s minus s to the power n minus 1 y minus a n minus 1 s to the power minus n minus 2 y, and so on up to minus a2 s y minus a1 y. So, this particular figure represents the differential equation which we just written. Now, the important thing which still is left is that how we will correlate the nodes which are adjacent to each other. So, how we will connect them? So, just previous case when we discussed that how x1 and x2 are related. So, this knowledge we just discussed will utilize in connecting the components. So, if you see the component at this side, x2 is connected with x1. How you are connecting? You are connecting with sy is connected with y with s to the power n minus 1 plus the initial condition for y, that is y t naught by s. So, this is what you got from the equation which we just derived. So, because if you see x1 is nothing but x2 by s into x1 t naught by s. In our case x1 s is y, x2 s is sy. So, what we will do? We will use that information and connect the adjacent nodes. So, in this way you can connect all the adjacent nodes with 1 by s and put the initial condition, because when you divide the nth order differential equation into n first order equations, you will have the equation as we discussed in this case. So, you will get these equations in Laplace domain, where you have initial conditions for each and every state variable. So, we will utilize that information and we will put the initial conditions of all the state variable and connect them with 1 by s. So, this is the final state diagram which you will get, and this will represent this particular differential equation. Now, let us take one example so that you can better understand. Let us see, there is one differential equation, that is d2y by dt2 plus 3 dy by dt plus 2y equal to r. Now, what we will do? We will equate the highest order term of the last equation to the rest of the terms. So, what we can write? We can write d2y t by dt2 is equal to minus 3 dy by dt minus 2y t plus r t. So, here we will have 1, 2, 3, 4 terms. So, we will create 1, 2, 3, 4 nodes. Now, this node is basically being extended to give you better clarity. So, you can add y with unit gain, so that you can have the clear understanding from the state diagram. So, we have added these 4 nodes. One is r, second is y t. So, you will replace with y. Third is dy by dt. So, you will replace with s y, and d2y by dt2 you will replace with s square y. Now, what procedure we followed previously, we will just use that procedure. So, the y is adding to s square y with minus 2 as a coefficient. So, we have minus 2 as a coefficient. dy by dt you multiply with minus 3 to add to s square y. So, we get these two connections, and r is having 1 as a coefficient. So, r is connected to s square y with 1 as a the gain. So, now what we will do, we will connect these two nodes with each other with the help of the integration function which we discussed. So, we will connect with 1 by s square y will connect it to s y with 1 by s, and plus the initial condition you have for y 1 t naught by s, and then for y we have y t naught by s as an initial condition. So, finally, you get the state diagram for the differential equation which we just shown in the slide. Now, the next question comes when you are asked to find the transfer function from the state diagram. So, what you will do? So, the transfer function between input and output is obtained from the state diagram by using the gain formula and setting all other inputs and initial state to 0. So, what we will do? We will set the initial states to 0, and then we will equate input to output. So, R s and Y s is obtained by using the gain formula. So, what we will do? We can write s square y equal to minus 3 s y. So, that is from this minus 2 y plus r. So, what you can do? You can club all y component in one side. When you club, you will get s square plus 3 s y plus 2 into y equal to r. So, this is what you get when you check the signals which are coming to s square y. So, when you sum up, you get this. Now, what is the transfer function? Transfer function is y by r. So, what you get from here? You will get, that is s square plus 3 s plus 2. So, basically the y we have already taken out. So, this will become s square plus 3 s plus 2 into y equal to r. So, y by r you get as 1 upon s square plus 3 s plus 2, which is nothing but the transfer function you have got from the state diagram. So, with this we can close our today's session, in which we discuss mainly the state diagram. Now, we will see next how we will use the state diagram to find out the state equations. Thank you.